Hello everyone, my name is Mourad Bouziani from the School of Geomatic Sciences and Surveying Engineering of the Agronomic and Veterinary Institute of Rabat, Morocco. Today, I am pleased to give this talk to present a study conducted by the team composed of my colleagues Hamza Shahba, Mohammed Attarid, and myself about the evaluation of 3D building model using terrestrial laser scanning and drone photogrammetry. I'll begin by giving the context and the objective of the study, and then I'll go on to present the methodology, the study area, and the equipment used. Finally, I'll present the main results obtained. Three-dimensional models of buildings represent important data sources for many applications. In recent years, advanced technologies have made it possible to create precise and detailed 3D models of buildings. The use of images acquired by drones combined with TLS acquisitions has brought many advantages to obtain complete and detailed 3D models. Few studies have investigated the quality of the fusion of point clouds obtained by drone images and terrestrial laser scanners for 3D modeling. The objective of our study is the evaluation of the 3D modeling of buildings and the extraction of structural elements from point clouds obtained using these two acquisition techniques, as well as the evaluation of the usefulness of their integration. The case study is the amphitheater of the Agronomic and Veterinary Institute, Hassan II. This building has an approximate area of 4,000 square meters. It is characterized by its oval outer shape and its annexes of different geometric shapes. The building has many doors and many windows distributed on its exterior. Two missions have been conducted. The drone shooting mission was carried out using the Phantom 3 Professional from the DJI brand. The shooting was carried out with the Sony Exmor RGB camera. A circular flight mission planned with the Pix 4D capture application was carried out, with a flight height ranging from 10 to 60 meters and images acquired every 6 degrees. The selected front and side overlap is 70%. For the terrestrial laser scanning mission, targets were used to ensure good consolidation of the scans. A total of 9 scanning stations were performed using the Faro Focus S350 laser scanner. Two missions were carried out, drone mission and terrestrial scanning mission. Points acquired by terrestrial laser scanning mission goes through the following steps: cleaning, consolidation, creation of the mesh, texture of the mesh model, and finally creation of the 3D model. For the drone shooting mission, the processing includes the following steps: the camera alignments, generation of dense point clouds, creation of meshes, generation of textures, and finally creation of 3D models. We obtain 2 point clouds from each technique. To allow the fusion of the 2-point clouds, an alignment step is necessary. This step is performed using the ICP algorithm, the iterative closest point. The transformation parameters of the 2-point clouds are calculated through the relationship between the corresponding matching points to satisfy the convergence precision. Then the translation and the rotation parameters between the 2-point clouds are obtained to complete the fusion process. The initial values of the iteration are determined by performing many tests. For the quality assessment, we realized a cloud-to-cloud comparison on the totality of the 2-point clouds obtained by drone images and by terrestrial laser scanner. To estimate the accuracy of the 3D model obtained, we compared the distances between the point cloud obtained by TLS, by drone images, and the merged point cloud to a reference mesh model using the cloud to mesh distance function. We then performed segmentation tests on the point clouds obtained from the drone mission and the TLS mission, as well as on the merged point cloud, using an adapted random sample consists RANSAC algorithm. We did the segmentation by varying the minimum number of points on different combinations of geometric shapes, such as planes, spheres, cylinders, and cones. The segmentation gives the possibility of extracting several structural elements of the building, such as windows, doors, and stairs. Here we can see the result obtained for the generation of the different point clouds and the modelization, 3D modeling. The model resulting from the drone point cloud lacks information on some parts of the building, especially in the entrance to the amphitheater, because of the distance and the angle of view of the aerial image. On the other hand, it gives a complete model of the roof of the building. The point cloud of the TLS gives the possibility to model the facades precisely and the entrance with a lot of detail. The merged model offers complete information on these two parts of the amphitheater. Besides, we can see the values obtained from the quality assessment over the cloud-to-cloud comparison and using the cloud to mesh distance mapping. We can see that we obtained a better quality for facades only using the TLS point cloud, but when we performed the integration of the 2 points cloud, the quality was improved for the 3-dimensional modeling of the amphitheater. The merged point cloud has been realized with a RMS error of 6 centimeters and an overlap of 100%. And we obtained an average deviation of 3 millimeters and a standard deviation of 2 centimeters. Here we can see the results, some examples of result of segmentation. And the table shows the quality of segmentation by computing the rate of points correctly detected in a segment in comparison with a reference segmentation. From these results, we noticed that the point cloud obtained from TLS gives a better extraction of the facade elements, such as windows, stairs, and doors. For the segmentation of this point cloud, we can clearly identify the different structural elements to be extracted for the facade only. However, we see that the point cloud obtained from drone imagery does not give quality requested on some parts of the facades, here the stairs and windows. But when we performed the integration of the two-point clouds, the results were improved, and the extraction is of a good quality over all the elements of the building and not only the facades. This results shows that the quality of the integration of the two-point clouds depends also on the complexity of the geometry of the structure to be extracted. For example, for the entrance, doors, and chairs and stairs of the building, which have simple planar geometry, we obtain an improvement compared to the two source point clouds. But it's difficult identifying the side windows and the other complex elements as they have complex curved geometry. In conclusion, our work consisted in the evaluation of the 3D modeling and the extraction of structural elements from point clouds from two technologies, drone photogrammetry and terrestrial laser scanning, as well as the evaluation of the contribution of their integration. Each technique has strengths and limitations. The integration of the two technologies improve the completeness of the coverage, which allows the modeling of the complex objects of this building. For the extraction of structural elements such as windows, stairs, and doors using the geometric segmentation by the Ransack algorithm, the combination of the two technologies, drone imagery and TLS, improve the segmentation results. This analysis emphasized the importance of terrestrial laser scanning and drone imagery in 3D modeling, and confirms the importance of complementarity between these two technologies to produce detailed, complete, and precise 3D models. Further experiments are underway to improve the integration of the two technologies for other types of buildings, for the evaluation of the digitization of buildings, and to generate digital BIM models. Thank you for your attention.